To continue where we left off with sequences, let's consider this theorem, the limit of a sequence using a function limit. So if the limit of a function, f of x is L, and it turns out that f of n is equal to the terms in our sequence, a sub n, for each integer n, then the case would be that the limit of a sub n has to also equal L. So this allows us to use all of our function rules and limit rules as long as our terms in the sequence can be written as a function. So basically, I like to think of this as a way to connect the dots. So we can think of this theorem like connecting the dots of a function graph and evaluating it only at the integers, and we're looking just at the integers. So when we graph a sequence, remember, it's just a set of dots. The inputs, the x's are just the integers. But if we could actually represent it as a function, then we can look at the limit of the function. So here's a little graph where we've basically colored in or drawn in, connected the dots of the sequence, and we can see that it's approaching some limit L. So here's how that would work. Let's just determine if the following sequences are convergent or divergent. So for these first couple, we'll just run through them quickly and then get into some more limit laws here. So determine if the sequences are convergent or divergent. A sub n equals 1 over n cubed. Well, if we think about f of x equals 1 over x cubed, then at each of the integers, f of n would be equal to 1 over n cubed. So we can use that theorem. And we know that the limit as x approaches infinity of 1 over x cubed equals 0. So the limit of this sequence of terms has to also equal 0. Okay, so that said, just to streamline this process of taking limits of functions, then we can say this. If a function f of x exists such that f of n equals a sub n on that set of integers, then we can just take the limit of f of n as n approaches infinity and apply all the limits for the functions. We're just doing it with a restricted domain. So we can do this. We can take the limit of f of n as n approaches infinity, just looking at it with a restricted domain. So this, we'll jump right into this. So here's another example. If we just take a sub n equals n squared, so the sequence of terms, so this would just be the sequence of terms if we were to write this out. This would be 1, 4, 9, 16, and so forth. This would be just infinity. It grows without bound. So if we were to take the limit of n squared as n approaches infinity, then of course that's just growing without bound, and that's going to be divergent. What we call is divergent. That is a specific type of divergence, though. Let's keep that on the screen there. That's a specific type of divergence. And we can say this, it's an unbounded sequence, meaning it just grows without bound. And so the limit as n approaches infinity of a sub n equals infinity, as long as for every positive number that is out there, m, there exists an integer so that the terms in the sequence are bigger than m as long as the index of the sequence is greater than n. So we still say that's a divergent sequence, but it's divergent in a really specific way. So just like with limits, we can capture that type of behavior with infinity or negative infinity. We can capture that behavior in a sequence by saying that the limit as n approaches infinity of the terms a sub n is infinity. All right. Okay, so I'm going to just run through these really quickly. These are just all the same limit laws that we had when we were in Math 30 in Calculus 1, but this time they're just in the context of sequences. So for instance, if we take the limit of two sequences, it's the same as looking at the sum of the individual limits or the difference of the individual limits. And if we have a constant, we can pull that constant out in the front. And the limit of a constant equals a constant. And the product of two sequences, if we take the limit of the product of two sequences, that is equal to the limit of the product of the two limits. And the same with the quotients and powers, so forth. Okay. All right, so those rules will apply as we're evaluating these limits, but they just stem from our Calc 1. This theorem, though, this one is these two theorems are fairly important and worth highlighting. If the limit as n approaches infinity of the absolute value of a sequence is 0, then the limit of the sequence has to also be 0. So this will help us deal with some things like oscillation or when we have a switch. So we can talk about that. And then the second theorem, if the limit as n approaches infinity of the absolute value equals L, and we have a continuous function, then the limit of f of the limit of the function evaluated at the terms is also equal to f of L. So this is also an important theorem that we'll utilize. Okay, so let's jump into actually evaluating some of these. So for this very first example that I want to look at here, the limit of n over 2n plus 1 is n, starts at 1, the index is 1. Now there are lots of ways, and I talked about this, discuss all the different strategies underneath this problem. There are lots of ways to do this, but the first thing that we'll look at is we could just consider the limit as n approaches infinity of n over 2n plus 1. And we can think about, well, what would that limit be? And we can do this because there is a function that exists, f of x, that is equal to x over 2x plus 1. This is a function that we can take the limit of. So, and we're just evaluating it, just as a reminder of why we're able to do this. Evaluated at n equals an integer. So we are essentially just restricting the domain of this function and taking the limit of that function. So as we do this, there's a couple ways we could do it. Of course, this does become infinity over infinity. So we have a couple of choices. We could use L'Hopital's rule. There's some other options here that stem way back from just the beginning of limit theory back in Calc 1. We could also just divide each term by n. That's another way we could do it. Or we could even use the fact that we have two polynomials and the degree of p equals the degree of q, some theory that was developed in Calc 1. So if we wanted to use any of those, just sort of take your pick, whatever you want to do here. But this does end up being, when we take the limit as n approaches infinity of n over 2n plus 1, what we end up with, if we wanted to, I think most of us have gotten pretty comfortable with L'Hopital's rule at this point, this becomes the limit as n approaches infinity of 1 over 2, which is, of course, just 1/2. And again, we could have used all of those same rules. This is the same result that we would get if we were to make a claim and talk about the fact that we're talking about a rational function of two polynomials of same degree. So the degree of p equals the degree of q. We could also say that. Okay, that's another way to say it. Okay, so let's talk about a couple more. So a couple different options on that one. Choose the way you want to approach these, and you can use L'Hopital's rule, but we have all of our other choices as well. Okay, so let's take a look at this guy next. So I have several examples to go through, but we're not going to have a chance to go through all of them on this video. I'll save a couple of them that we can talk about during the class sessions as well. So this particular one obviously has a switch. So this first example I've highlighted here, a sub n equals -1 to the nth. So if we were to write this out in the first few terms, we would have -1, 1, -1, 1, and this would go on and on. Now, we have shown this before and talked about how this is going to have to oscillate. Even if we were to graph this, even if we were to think about what this looks like graphically, we can see this oscillation. So if this were 1 and this were -1, 1, 2, 3, 4, 5, and so forth, going on and on. If we were to actually graph this sequence, at 1 we're at -1, at 2 we're at +1, at 3 we're at -1, and this is going to go on and on and on. And back to just the actual definition of the limit, the exact definition of the limit, given any epsilon greater than 0, there's no way that we can smash these terms, that these terms will eventually be within an epsilon neighborhood of any finite value. They're just going to continue to bop around between -1 and 1. So we can say that through sort of a graphical approach. We could say that this diverges, and our justification would be because it oscillates because of oscillation between +1 and -1. That's some justification there. We could also go ahead and rely upon that if we were to take the limit as n approaches infinity of the absolute value of this particular sequence. Well, the absolute value of -1 to the nth is I'll show this out in the steps what happens here with the absolute value, but when we take the absolute value, that can actually run inside, and then we're taking the absolute value of -1 to the nth. Well, that of course is just 1, and 1 to the nth is 1, and the limit of 1 is 1. So notice that the absolute value of the terms is 1, and so the terms themselves are approaching 1. So the terms, there's a very mathematical way to say what we just set up above. The terms approach 1, but they oscillate in sign. Oscillate in sign. Okay, there's another way to say it, so it's another way to show it. Okay, so here's also another way we could talk about it. We could say, let's take the absolute value of those terms and show that they approach 1, and then throw a switch on them. And if they're approaching some finite number other than 0, and then you're switching the sign, then they're never going to have a convergence. So we say this diverges. Okay, let's look at another example. So let's take this guy here. So if we were to take the sequence of terms n over e to the n, and think about that. So let's take the limit as n approaches infinity of n over e to the n. Well, this of course is that infinity over infinity again. And we can think about the fact that right here, and we're going to talk about this types of functions here. We've got a polynomial n on the top, and we have an exponential function on the bottom. So that exponential function, we're going to talk about growth rates of sequences here in just a second, but that exponential function on the bottom is definitely going to dominate these terms. And we can show that directly with L'Hopital's rule. Rates of change. So if we take apply L'Hopital's rule here, the limit as n approaches infinity, of course, is 1 over e to the n, and that is 0. So this guy converges, this sequence converges to 0. Okay. All right, let's take a look at another one. So how about this guy? So we've got a switch. So we've got -1 to the n over 2n plus 1 from n equals 1 to infinity. So this is similar to what we looked at up above here. We have oscillation, clearly, but what is that oscillation going to do? And for that, we definitely want to think about, well, what's the absolute value of this sequence, and what's the limit of that? So let's take the limit as n approaches infinity of the absolute value of these terms. So what happens there? So if we take the limit as n approaches infinity, the absolute value of -1 to the n times n over 2n plus 1. Well, that absolute value, and it's something that we will utilize and look at quite a bit, but when we take that absolute value, what happens to that switches, it just becomes +1. So we're just going to be looking at the limit then as n approaches infinity of n over 2n plus 1. And that limit, of course, is 1/2. Okay? Now, we can show that. We can show that limit is 1/2. We can use either L'Hopital's rule. Here, I mentioned this above in a previous example. Here, I'm going to just say that the degree of p of x, p of n actually, p of n, I'm going to just utilize some algebra facts here. The degree of p of n equals the degree of q of n. And if the two degrees in the polynomials here, so if this is our p of n, just as a reminder from Calc 1, and this is our q of n here. If those have the same degree, then the limit as we approach infinity is going to be the ratio of their coefficients. So 1 over 2 is where we're getting that. So I'm going to utilize that fact here. So the limit of the absolute value is 1/2, but don't get that confused. That's not the limit of my sequence. My sequence has a switch on it. Okay? So then we have to say, okay, well, that means that as we head towards infinity here, with that switch on it, the odd terms are actually going to be approaching -1/2, and the even terms are going to approach +1/2. So we can say that here. We can say, therefore, this particular sequence is diverging by oscillation as the even terms approach positive 1/2 and odd terms approach negative 1/2. So we have oscillation here. So the terms are approaching, they're not always just positive and negative 1 like the previous oscillation example, but these ones are approaching if we think about actually what that looks like graphically, just if this were 1 and this were negative 1, so you've got your 1/2s in here, the terms are going to be approaching, so they're not exactly there, but every other term, turns out actually the odd terms are negative 1s, 1/2s approaching negative 1/2, so we've got oscillation that's kind of doing something like this as we head out towards infinity, as we let n approach infinity. So this has to diverge. Okay, one more example. And I have a couple other examples in here, and I'm going to just leave them here and we can revisit these and do a few more examples in the class session, but I wanted on this video to get a couple of examples in. So let's take a look at this guy. So what if we were taking the limit of 1 plus the cosine of 1 over n as n approaches infinity? What happens here? So, well, what does happen here is we take the limit as n approaches infinity of 1 plus the cosine of 1 over n. So what happens as we approach infinity? Well, this, notice, is a continuous function, cosine. So note here that the cosine of x is continuous. And way back at the beginning of this video, we talked about all those theorems, and one of the theorems stated that if you have a continuous function, that you can run the limit into the continuous function. So we can actually say, well, this is the same as looking at 1 plus cosine of the limit as n approaches infinity of 1 over n. All the same things that we've done with continuous functions before. The fact that 1 over n has a limit and cosine is continuous allows me to actually run that limit inside of the continuous functions. So we can go right inside. I'm going to go ahead and not write that notation. I just wanted to mention that we are utilizing that theorem right there when we do this. And we come in here and we just say, okay, well, the limit of a constant is a constant, so that'll be 1. The limit of the cosine of 1 over n, well, 1 over n, as n approaches infinity, this is actually approaching 0. So just like we take limits, this becomes 1 plus the cosine of 0. And the cosine of 0, of course, is 1. So 1 plus 1, this ends up having a limit of 2, which means as we head to infinity, these terms actually converge. They are approaching that finite value. This converges to 2. They're approaching that finite limit of 2.